Good morning, everyone. Welcome to the fourth and final day of the Chennai Symposium on Gravitational and Cosmology. We have an exciting set of talks ahead through the day. The first session this morning will be chaired by Rajesh Naik from ISA Kolkata. Over to you, Rajesh.
Okay, thank you, Sriram. So let us start the first session. There are interesting talk. First talk is by Debaprasad Maity. He is going to talk on the gravitational reheating and its observational effect. Deva, you have 30 minutes. I will warn 3 minutes before your time, and then 5 minutes we have for discussion. Here.
Debu, please go ahead. We are not able to hear you, Debaprasad.
He's unmute or he's mute, I think.
Please unmute and speak, Debaprasad.
Yeah, you should be able to do it yourself.
Okay. Now is it visible?
Yeah. Yes, it is visible. Please go ahead.
Okay. First of all, let me thank the organizer for giving me this opportunity to give a talk here. So my today's talk will be based on the reheating phenomena, which we have been working on this topic for quite some time, and we have many collaborators that have already mentioned here in this in the below. So what I will be talking about is essentially the effect of reheating on the observable sector, and also in the inflationary sector, and the specific model of reheating that we'll be talking about, gravitational reheating, and we will be essentially describing what this gravitational reheating means. Okay, let me start by asking this question: how the present state of our universe has been created? So this question is, anyway, now we all know probably quite well, in the sense that over the last almost 100 years of observation, theoretical development led us to this beautiful picture of evolution of our universe. So, so basically it says that as we go backward in time, starting from the cosmological sector, cosmological constant will get matter, and then radiation, and then inflation. So this is what is that we know from our from the large number of cosmological observations, as well as the theory, and then in parallel there was theoretical development, which gives you this very good picture of the current universe. But today's talk will be essentially focused, my today's discussion will be mostly focused on a particular phase which appears in between this inflation and radiation, which is the reheating. And this is extremely important that you might understand, because if you have inflation, then naturally you would expect there has to have some mechanism such that you would get all the energies that you see today in terms of the present in terms of the present content of the universe. So what does it do? So inflation essentially creates a huge, exponentially large space, homogeneous space with almost zero temperature universe, where we have the background homogeneous energy, which is filled by energy, which is essentially the inflaton energy, and then on top of that there are small fluctuations. So this is the state that is being created by the inflation. And then what reheating does in between, so so basically in between, okay, I don't think okay, anyway, so in between we have this reheating phase. What it does, it essentially creates it transforms this cold and extremely homogeneous with the tiny fluctuations into a very hot universe, and with again the same this tiny fluctuations. So basically what happens, that inflaton is going to be transferred into the hot soup of plasma, hot soup of energy of radiation. And then based on the wherever the fluctuations is there, so there you will have according the transfer. So basically you start with the very cold homogeneous with a small fluctuation universe to a very hot homogeneous with a very small fluctuating. So this is what this reheating does. Now, and how do you do this process? This process, as you might understand, as you can clearly, this, you can see that this process is not very simple. I mean, it's very extremely difficult process. I mean, you can see this this kind of process is similar process that we see in a waterfall diagram, where it is exactly like inflation. In the top of this waterfall, you have this inflation, and then you have this waterfalls, and then you get a complicated process of formation of bubbles and all steams and everything. So what is the conventional mechanism that you do this reheating? It is essentially conventionally, when you try to understand the reheating process, it is extremely complicated, and it's a non-perturbative process. That is what we believe. That is what so far the theoretical development has been. That's a highly non-trivial, non-perturbative, non-equilibrium process. And mostly what people have done over the last many years is essentially in terms of non-perturbative aspects, mostly theoretical. And then recently there are works people have been trying to understand the reheating process through perturbative decay of inflator, and then try to connect with some observables that we see today. But it's very recent. From the observational perspective, actually very little attention has been paid, particularly this phase. But I think we can understand, but this phase is extremely important. But what is the reason that little attention has been paid specifically in the observation front? Is because it's very complicated, and there is equilibration process happens because it starts from non-equilibrium phenomena, and then finally at the end you have to have this equilibrium distribution of matters, this radiation, and which essentially erases all the information whatever has happened before. And then it is large uncertainty in the sense that how this inflaton is going to be decayed into the radiation is completely unknown, because you can have infinite possible, large number of possible channels through which inflaton can decay. And so all this, because of all this, it's extremely difficult that they identify observable which can be observed in the present universe, which can shed light into this particular dynamics. But we all know that if you observe the present universe, what are the quantities that you see? We see background plus fluctuation always. But of course, we don't see inflaton. Of course, if you model the inflaton to be some other as a dark energy or dark matter, which is not very successful. Otherwise, what you see in our present universe is a background plus fluctuation, where background is either radiation or dark matter. And then on top of that, you have this tiny fluctuations. And then you can have also the primordial gravitation. These are the present observable universe. And of course, and the very important point is that all this has a very clear proportions. How much should be the radiation, how much should be the amount of dark matter and all that. So this is very clear proportion is also there. So that means you start with inflaton, but finally your reheating will give you this proportion. What should be the proportion that we see here? So so reheating gives us right proportion of all this, because that means how much of the inflaton will convert into the radiation, how much of the inflaton convert into the dark matter is essentially reheating is decided. So that's why this information must be imprinted into background plus fluctuations in some way today. This has to be there. It should be there in some, this information of this complicated reheating process should be imprinted in this background as well as fluctuation. That is what we should expect. So in terms of inflation, let me just, because this is what we'll be using in our analysis anyway. So this is the inflation that we, the parameters that currently we we are in with. So this is essentially a plot with in primordial spectral tilt and tensor to scalar ratio, and over the years it does not change much, except the fact that now we have a little lower limit on the tensor to scalar ratio. Otherwise, the central value of the NS and the range of NS that is allowed is still pretty much the same. And these are the various models that are there in this figure. Okay, so now what is the questions and what is the plan that I'm talking about? Reheating happens, that of course is we know, and inflation energy transferred into all the visible fields such that we obtain the present state of the universe. As I mentioned, this present state is very unique. It is I would say it's like you have to have a very right proportion of the radiation, and you have to have right proportion of gravitational dark matter. You have the right proportion of visible matter. So such information must be imprinted in the background and fluctuations in some way, because reheating, some information about the reheating, how that process happens, should be there. And then the question is where and how such information are imprinted, and how do we proceed to identify them? These are the questions that is very important to understand. And of course, in a simple-minded picture, why that is important? Because we know there are all these puzzles, the dark matter puzzle, baryogenization, there are all the other things which we don't really know. Okay, so that means we hope, because reheating is the only phenomenon which actually gives you you transfer your energy from inflaton to all the matter field that you see today. So that means reheating may give you answer all these questions. So now the plan is to talk about the gravitational reheating setup, of what you mean by gravitational reheating, and then its prediction constraints in terms of observables and theories. And then finally, I will conclude. Okay, before I directly get into the gravitational reheating, let me just briefly talk about reheating phenomenology, meaning in the sense that it is essentially same as that what I will talk about. This is essentially will be setting my stage towards the gravitational reheating. So what we do, the usual approach. So usually gravitation, this reheating phenomena is done by taking some phenomenological Lagrangian for the inflaton coupled with all the matter fields. But moment you introduce this coupling, you can have all sorts of coupling. And also you don't really know how many degrees of freedom are there in the system at that very high energy scale, because the process that is happening is of the order of 10 to the 13 to 15 GeV. So at that energy scale, we don't really know whether this is only the standard model fields, or there are a lot of other fields that as you go higher and higher energy may have many other fields. That means you have infinite possible couplings, or a large number of possible unknown couplings, which can if you try to describe this phenomena through this. So you have large number of possible couplings, and then moment you introduce those couplings, you may have a complicated phenomena called parametric resonance, which is essentially coined as preheating. And then preheating will not be sufficient to finally end the reheating process, so you have to introduce also perturbative reheating. But of course, everything can be described in a single framework where you introduce all these couplings. And so that means you have too many parameters to describe the whole system. So that means the moment you have a large number of parameters in that space, it's just essentially we are lost. I mean, what to predict, what should we look for? And in addition to this, these couplings, you always have this gravitational decay channel. What is this decay channel? Essentially, because all the matter fields will definitely gravitationally coupled with the inflaton, because it is universal. So that means this decay will always be there. So that means in addition to this, all these couplings that we have, we consider, in addition to that, we have always this gravitational, which is universal, has to be there. And remember that the process that I'm talking about is of the order of 10 to 15 to 13 GeV. Okay. So it is extremely high energy process. So it is very difficult to ignore that particular gravitational decay as well. But gravitational decay, if we assume all the couplings that we have of the order one coupling, this alpha, because all this here, whatever interaction that I have written down as a dimensional span coupling parameters, typically you would expect that the value should be not very, it should be small, of course. But gravitational decay channels were also ignored, was always ignored because of the obvious reason, because it's highly suppressed by Planck mass. So you would expect that compared to all the other interactions, this gravitational decay will be suppressed. Anyway, so it would give you nothing. That is what usually people assume, that nobody has studied it before, because it was implied, given the fact that you have all sorts of couplings with the other fields, you would expect the gravitational decay will not be important. But can gravitational decay, the question that you have asked, can gravitational decay reheat the universe? This is what we asked, and let us try to see what happens. Okay, the first question that we are asking, why at all should we take such scenario? Of course, because as I told you, in the observational front, reheating was not systematically studied. I mean, people have studied reheating, taking coupling, and then you look into what happens and all that. But systematically, it has not been studied looking at. Hello? Yes?
Sorry, Debu, there was someone who had unmuted their microphone.
Okay.
Yeah, sorry.
So it has been systematically studied. So it is better if we want to really predict something, or you want to really see some imprints of this particular phase, we have to go systematically. So now if you start with the too many parameters, it's impossible to predict anything, because you can't say anything. So that is why the reason that we are trying to see, let us look at first the gravitational decay, if at all it is possible to reheat the universe, and then systematically you can proceed. How do you proceed it? That is the phenomenological questions, of course, because we have to then construct by using some symmetries and by using some UV theories, that how to systematically couple this inflaton field with the visible sectors. So let us not worry about this particular phenomenological, because first question that we need to ask, whether at all this gravitational coupling will actually reheat the universe, because this is because it's extremely weak coupling. It is extremely difficult that you have some parameter space where this gravitational reheating is possible. But anyway, we can give you a simple argument that this kind of scenario where you have this only gravitational coupling and all alphas are 0, if you introduce some symmetries, because if you have a lot of parameters, then easy way to reduce number of parameters is to have some symmetry, like Z2 symmetry. If you immediately impose the Z2 symmetry in the inflaton sector where the inflaton is 5 and a visible sector in such a manner, then immediately we'll get that this alpha 1, alpha 3, alpha 4 will be immediately 0. And we all know the SIP symmetry plays very important role for the inflation. So now if we additionally impose, or if we impose even just SIP symmetry, then we'll find that the large number of coupling will automatically be 0, because SIP symmetry automatically gives you only derivative coupling. And if furthermore, I have written few operators which are possible in the SIP symmetry, and we'll find that gradually, if you more and more symmetry, which are not like ad hoc. I mean, you can get some kind of symmetry in particle physics model. And if you assume both the symmetries, let's say Z2 and SIP symmetry, they will find is all these parameters that I have written down at the beginning will be essentially setting to 0, and we land up with the operators which are actually higher dimensional than the gravitational coupling. So automatically, you would expect, if we try to construct a model of inflaton from phenomenology, then Z2 SIP symmetry will be essentially saying that gravitational coupling will be dominant channel to reheat the universe. So this is, we have not studied in detail, because we have started, because our first priority was to see whether this gravitational reheating was possible without all the alpha i's, all the ad hoc coupling to be 0. Okay, here is the setup. I mean, it's very simple. Because we have this gravitational coupling, we will not have those complicated parametric resonance and all, because parametric resonance, you need to have a direct coupling with the inflaton field, such that the daughter particle who is coupled with the inflaton will see the oscillating inflation. So here what we'll have a S-channel decay, that you can see the Feynman diagram that I have drawn, where 2 inflaton goes to all the fields that you can think of. Okay, so that is the dominant channel. That is the only channel that will contribute to the this transfer of energy. So you can write down all these equations, and these equations in a simple-minded in the Boltzmann framework. So what additional thing that I should emphasize here is that whatever is there, the setup that I'm describing here does not depend on what kind of physics, what kind of degrees of freedom are there in the system, whether you have large number of degrees of freedom in the system. We have divided into this radiation, massless, because it's a gravitational coupling. Gravity only see the mass, so it will be divided into two sectors. One is massless, and I identify massless to be radiation and massive to be dark matter, because at that high energy scale we assume that all the sectors can be divided into these two sectors. So you can see here that this description does not depend on even what kind of particle content are there in the universe. It can be anything. I divide that into just massless and massless. So that's why it is a universal coupling, and it also giving you, it is also saying that it does not at all depend on what kind of physics or complicated physics are there in the physical sector. So when I'm saying physical sector, I'm talking about all this radiation and dark matter, okay, and the inflaton sector. So I divide these two sectors, inflaton sector and the visible sector. So that means it doesn't depend on any complicated physics, except of course if there is a coupling between dark matter and radiation, there will be some changes. I will not talk about that, but we have done this analysis, and but for the timing, let us just restrict to that there is no dark matter coupling with the radiation. But apart from that, there is no dependence. An important point that you can see here, that you have only three parameters to describe the whole universe. One is the dark matter mass, another is the equation of state of the inflaton, and the initial energy of the inflaton at the beginning of it. So these are the three parameters which will completely fix your present state of the universe. And it's extremely interesting that we don't need any parameter to fix, if at all, this inflaton reheating happens successfully. Okay, so now unique initial condition that I already mentioned, these three first lines, and then we have constant. Now, how do you identify? How do you say what state that you want? Because we know the present state of the universe. Now, what is the present state? How do I give you? Because essentially, present state of the universe give you some constants while solving the Boltzmann equation that I mentioned before. So, what are these constants? One is entropy conservation. I say there is no entropy production after the reheating, which is a reasonable assumption. And then you have the reheating, the radiation temperature at the present time, which is T0. And then present dark matter abundance, you have to satisfy. And another two important point that you have to satisfy is that universe must be radiation dominated for the reheating temperature must be greater than BBN temperature, because a reheating should end after the, or universe should at least have radiation domination when the temperatures are around BBN. So that is the lowest bound of the reheating temperature. And then upper limit of the inflation energy density, because that will be coming from the observation of Planck, because Planck will give you, because it has not observed the R, so it will essentially give you the upper limit of what could be the maximum value of inflation energy scale. So that means this is my present, this constant is essentially my present state of the universe, because this will completely fix the present state. So that means all this present state of the universe will be fixed by these three parameters, as I told you: dark matter mass, equation of state, and the energy density of inflaton. I mean, it is so. Okay. Now,
Debaprasad, you have 3 minutes.
3 minutes. Okay. Okay. So now let us talk about what the results. Model independent predictions, as I told you, because my parameters only, we have three parameters: m, omega phi, and my inflaton energy. So so let us give you the straight away the result without talking about any inflation models, except the assumption that I already mentioned here, that slow run inflation. This is the only assumption that I made, but we have not made any assumption about the inflation. But we'll see a surprising prediction of if I assume the gravitational universe is reheated by the gravitational reheating. So universe must be radiation dominated. This constraints at T greater than TRE immediately, and the upper limit immediately gives you that your HN should be within 10 to the power 9 to 10 to the power 13 GeV. You cannot go beyond that. And reheating temperature automatically fixes within this 10 to the power 8 to 10 to the minus 3. And inflation equation of state has to be 0.6 to 0.9. So your inflaton, if inflaton equation of state, which is essentially equation of state during reheating, has to be 0.6 to 0.9. It cannot go beyond that. And then entropy conservation and present dark matter abundance will immediately give you that your E-folding number, inflationary E-folding number. So by studying the reheating, we found that the inflationary E-folding number has to be 60 to 63 within. It has to be within 60 to 63. And the dark matter, if you are talking about fermionic dark matter, it has to be within 10 to the power 5 to 10 to the power 8, which is very narrow range of dark matter mass. All other range will be ruled out and not allowed. And then if you are talking about bosonic dark matter, it is even smaller, within 50 to 1000 electron volt. So you cannot have dark matter mass to be greater than this 1000 electron. So it's extremely interesting. And now if I take this scenario, because as I told you already, gravitational, this equation of state actually plays very important role in the gravitational wave. Now, what kind of observable effect it can give you? It can give you a very precise spectrum of the gravitational wave, which is in the right hand side that I plotted. And this is the precise gravitational spectrum that you can see. So it predicts that a very precise gravitational wave spectrum. And so you can see there are a lot of observational activities that is happening around this range, where if you increase the sensitivity around the line, then you would expect to see that sort kind of spectrum of the gravitational wave. And it immediately, and this tilt of this gravitational spectrum is essentially that is telling you what should be the gravity index of the gravitational spectrum, and the index of the gravitational spectrum should be within 0.57 to 0.9. So it is very precise prediction if we assume gravitational wave. Okay, now just give you just one or two, hopefully. Okay, so let me go to let me just not talk about this particular slide. At least let me mention one thing. What we conclude from this analysis is that apart from predicting very precise value of the dark matter mass, very precise range of dark matter mass, and the gravitational spectrum, it also limits what kind of inflation it should give you this kind of consistent waves. And this is the last slide that I say. So basically, we took a specific model called alpha attractor, and we found that if you look at this right figure where we have plotted the NS versus range, within this very small range of NS, it is allowed. And alpha has to be within 1 to 10, because alpha attractor, you have this parameter alpha. Alpha cannot be anything, n cannot be anything, lambda cannot be. Everything is fixed within a very specific range. So alpha has to be within 1 to 10, and NS has to be within very small range. Then all the other NS will not be allowed if we assume gravitational reheating to be the reheating mechanism. And of course, these are the various dark matter mass that we see. I think let me end by saying this, that if we assume the gravitational reheating the only reheating mechanism, then it will give you very precise range of dark matter mass within which it is allowed. It gives you very precise value within a very small range of NS within which and that all too is actually within the 1 sigma or 2 sigma range of NS experimentally observed by Planck. Okay, I think with this, let me end. Okay, so what he proposed, that gravitational reheating scenario is extremely important, and which is it has very definite predictions, and it gives that it actually selects a very limited class of inflationary models. It does not fit with the all sorts of inflationary models, and within an E-folding number is very precise within 62 to 60, narrow range of NS value, and it also predicts very narrow range of dark matter mass, low reheating temperature, and unique gravitational wave spectrum, and steep reheating equation of state. If we detect away from this, then you immediately say that gravitational reheating should not be the dominant channel to reheat the universe. And of course, the systematic inclusion of interaction that I was talking about is important in order to see more observables or more constraint on the theory itself. Okay, I think with this, let me end. Thank you very much.
Okay, thank you, Debaprasad.
Yes.
Any questions? Now it is open for questions.
Rajesh, Kandu has a question.
Yes.
Yeah,
Yes.
go ahead. You can unmute yourself and go ahead.
Yeah, thanks a lot. Very interesting. But I
Yes.
have some fundamental confusion. And
Okay.
it's just because I am probably not familiar with it. I thought what you were saying right in the beginning was that the whole process is because of coupling of the metric perturbations
Yes.
with the momentum tensor.
Yes. Yes.
But then afterwards, this metric perturbation never came into your picture anywhere. Because always
This metric,
going into SS and all those kind of reactions.
I mean, this actually, okay, so I think I have not gone into detail. Yes, this metric perturbation will naturally appear during the process also. Like you can have this radiation, you produce radiation, then you produce dark matter, then they will be, because it's a very high energy process, they will also be coupled through gravitational with H mu metric perturbation. We have also included that in our analysis. We found that that is also not giving anything new.
No. So what is gravitational reheating? Then I'm completely confused. Where does
What is?
come in?
Sorry, hello?
The question is, what is gravitational reheating? What do you refer to when you say it is gravitational?
Okay, when I'm saying gravitational reheating, I'm saying is this one. So this the first this when I'm saying gravitational, I'm saying the reheating process. I mean energy of the inflator going to all the matter field through this H mu, which is this process that I already this Feynman diagram, where phi goes to all the fields, be it dark matter or radiation, through this red dotted line, which is my H mu.
Sorry, I can't see. Oh, you mean the below one? Okay.
Yes. This Feynman diagram that I have drawn, which is the S-channel diagram, where you have phi goes to all the fields through the H mu line.
But then you have to quantize gravity, right?
You have to quantize
gravity.
Yes, this H mu is quantized. Yes, this H mu is quantized because it's a fluctuation. We have this background, and then on top of that H mu, which is a linear fluctuation, that fluctuation is quantized. Yes.
But there are no blow-ups of any kind.
No, I mean this process, there is in this S-channel process, there is no blow-up.
I see. Okay, interesting. I'll have a look. Thank you.
Okay, we may have time for one quick question. We are already running a bit late.
Can I ask a question, Rajesh?
Yes.
Sriram, go ahead.
Yeah, but I'm a little confused about that, like Kandu is, look, you are simultaneously talking about some, classical gravitational waves that have already been produced during inflation and which are, sort of evolving during this epoch. On top of it, you have these perturbations in, quantum fluctuations in H mu, which are coupling to your inflaton. Is that correct?
Yes. Yeah. So basically what happens, since you have this energy, let's say you have this phi particle, and which has energy of the order of 10 to the 13 GeV, and they can, through this process, through this interaction that I have written down H mu, Ti mu, it will, that 13 GeV to 13 GeV inflaton can annihilate into the graviton, which is of the order of, again, 13 GeV, and then that graviton can again decay into the standard model, or all the matter fields that we are talking about.
Okay.
I mean, that process will anyway happen at that energy scale.
I understand. Thank you. Thank you, Debaprasad, for the clarification.
Yes.
There is Raghavan who has a question, Rajesh.
Yes.
Please go ahead, Raghu.
Yeah. So I think it's all related to the same question. How do you get 1 upon m Planck squared S squared d mu phi as your interaction? I mean, just
Yes.
coming from S mu, T mu nu I,
Yes.
I can see the T mu nu for phi may have will be d mu phi, d mu phi. The T mu nu for S would be something m squared, s squared, or something of that sort.
Yes, I
So
understand.
there should be some other, mass scale also coming in here. And then the propagator got replaced by 1 upon p squared or some.
So if you look at that interaction, so let's say you have this del mu phi kinetic term, and then you have g mu nu del mu phi, then g mu nu can be g mu nu background plus h mu nu, and then h mu nu, t mu nu, you will have this coupling. And then why 1 over mp? Because if you expand your curvature tensor R, then you will get a kinetic term which is del mu h, and then you canonically normalize that kinetic term, then naturally you will have this 1 over mp. And this one is yes.
Sorry, go ahead.
Yeah, I mean, I'm saying there is no free parameter here.
No, I'm saying in the T mu nu for S,
yes,
it would not just have been s squared, no? There would have been something like some other mass scale there.
Yeah, I mean, this T mu nu contains your mass, and if you take just free Lagrangian, then you have this kinetic term plus mass. Yes, that because we have taken mass also, because you have this T mu nu contains mass as well as yes, and that mass we have already taken into account.
No, that the m squared or whatever energy scale squared going along with s squared would also show up in your effective coupling between s and phi. So wouldn't that be one more parameter? And probably you're integrating out some intermediate particle, or whatever it is. I mean, so
I'm sorry to interrupt Raghu and Debaprasad. Maybe we can chat during the coffee break. We can remain online and chat.
We can take this offline. Maybe during the chat. Let's continue with the session. So thank you, Debaprasad. Interesting talk and a lot of questions with it. So let